Welcome back to The Explainer. Today, we're stepping right onto the bridge of a ship. You know, long before the era of automated digital sensors and satellite feeds, seasoned navigators were out there reading the weather using incredibly precise, purely mechanical tools. We're going to demystify these analog, shipborne meteorological instruments that have quite literally guided vessels safely across the world's oceans for decades. Let's get right into it.
Here is the roadmap for our tour today. We'll start with the Mariner's weather station as a whole, then look at measuring pressure with aneroid barometers, tracking historical trends with the barographers, gauging humidity with hygrometers and psychrometers, checking out the classic mercury barometer, and finally taking the sea surface temperature.
Starting off with Section 1, the Mariner's weather station. We'll begin by surveying the essential toolkit every mariner absolutely relies upon.
Okay, think of this as the ultimate data-gathering toolkit. A proper vessel's meteorological station isn't just one single tool. It's a whole collection of robust instruments designed to measure pressure, humidity, wind, and temperature. And here's the kicker. They have to do all this despite the chaotic, constant motion of the sea. Between the engine vibrations, the corrosive salty air, and the rolling waves, these tools have to be both incredibly tough and highly precise. It's a real balancing act.
Moving right along to Section 2, pressure, specifically the aneroid barometers. Let's look at a true staple of the ship's bulkhead.
Take a look at the inner workings of the device in your screen. The word aneroid essentially just means without liquid. So, rather than using a column of mercury or water, this instrument actually relies on a partially evacuated vacuum drum or capsule. Because it's practically a vacuum inside, as the atmospheric pressure outside changes, it physically alters the shape of this little capsule. And there's a strong internal spring that prevents the box from collapsing entirely under the weight of the air.
It's a brilliant piece of macro-to-micro engineering, really. As the invisible weight of the sky presses down, that capsule deforms. Then, a mechanical lever system magnifies this tiny, almost imperceptible movement. Finally, a super fine chain transfers that tension to a pointer spindle on the dial. Fun fact, in practice, sailors will actually tap the glass face of the barometer gently before reading it. Why? Just to overcome any slight lingering friction in those tiny levers and chains.
Now, if you need serious pinpoint accuracy, we're talking down to 1/10 of a millibar, you step up to the precision aneroid barometer. This instrument replaces that simple mechanical dial with an electronic circuit featuring a miniature cathode ray tube, or CRT. Plus, it's usually mounted on a special anti-vibration bracket to make sure the ship's heavy engines don't throw off the reading.
Using this precision tool isn't just a quick glance. It requires a very specific, meticulous ritual. The navigator depresses a switch and rotates a micrometer head until the magic eye in the CRT shows a perfectly continuous line. Once that unbroken line appears, then, and only then, they carefully read off the pressure in millibars. It's a great reminder that collecting accurate, actionable data at sea isn't passive at all. It's a highly active, procedural discipline.
All right, Section 3, tracking trends with the barograph. Because knowing the current pressure is great, but tracking its historical trend is what actually keeps the ship safe.
Let's see how this principle scales up with the barograph. It uses the exact same vacuum capsule principle as the aneroid we just looked at, but instead of moving a pointer on a dial, it attaches the lever to a little pen. And this pen draws a continuous trace, called a barogram, onto a slowly rotating drum. To counteract the ship pitching and rolling, those capsules are damped with silicone oil, kind of like shock absorbers for the pen. The drum itself runs on a super reliable 8-day clockwork mechanism that the crew has to manually rewind every week.
So, the absolutely crucial point here is that this continuous trace allows the navigator to instantly determine the barometric tendency. You aren't just seeing the pressure right now. You are seeing exactly what the pressure has done over the past 3 hours. This specific 3-hour window is universally recognized in maritime meteorology as the golden metric for forecasting approaching storms. By observing the trace on the drum, mariners can easily compare the current pressure to where it was 3 hours ago. Is it rising steadily? Is it falling then rising? Or is it dropping rapidly? Identifying these specific patterns on the bar graph paper gives the officers on watch precious, actionable time to batten down the hatches if a severe low-pressure system is closing in.
Next up, Section 4, humidity, featuring hygrometers and psychrometers. We're moving from the heavy weight of the air to its hidden moisture content.
To measure humidity, sailors don't just rely on a single sensor. They actually use 2 thermometers side by side. The first is a standard dry bulb that simply reads the ambient air temperature. The second is a wet bulb. This one has its base wrapped in a clean muslin cloth wick that's dipped in distilled water. As water evaporates from that cloth, it draws away latent heat, which physically cools the wet bulb down.
The difference in temperature between these two bulbs is what meteorologists call the depression. Now, to ensure these readings are perfectly accurate and unaffected by direct sunlight or the intense heat radiating off the ship's steel hull, these thermometers are carefully housed inside a white, louvered wooden box called a Stevenson screen. They usually mount these out on the open bridge wings to get the cleanest air possible. Here is where the data becomes strategic. Once the navigator has the dry bulb temperature and the wet bulb depression, they consult a specified meteorological table. Cross-referencing these two numbers reveals the relative humidity and the dew point. Now, why does this matter to the ship's executives? Cargo preservation. Knowing the exact dew point dictates when the crew needs to ventilate the ship's holds to prevent devastating cargo sweat from ruining millions of dollars worth of goods. Alternatively, if the air is just dead still, mariners use a portable sling psychrometer. An officer will take this instrument over to the windward side of the ship, making sure they're out of the sun, and literally swing it around by its handle. This manual rotation forces an airflow right over that wet cloth sock, inducing the necessary evaporation to get an accurate reading.
Moving to Section 5, the classic mercury barometer. Let's step back for a moment to the oldest yet fundamentally standard method of measuring atmospheric pressure on the seas.
The classic mercury barometer is an exercise in pure, undeniable physics. It works by literally balancing the weight of the atmosphere pressing down on a small cistern of liquid mercury against the weight of a column of mercury being pushed up inside a sealed glass tube. When atmospheric pressure is at a standard level, that column of mercury stands exactly 760 millimeters high. No electronics needed.
But here's the catch. Raw analog data in this form is never perfect straight out of the tube. Mariners have to rigorously correct their mercury readings. They apply mathematical corrections for the ship's height above sea level, adding about 1 millibar for every 10 meters of elevation. But they also have to correct for local gravity variations based on the ship's current latitude, and even account for the temperature-driven expansion of the liquid mercury and the glass itself.
Doing that much intense math every single time you want to check the pressure? Yeah, that gets tedious. So to simplify this, navigators use a clever mechanical attachment called the Gold slide. Invented by Colonel E. Gold, this specialized slide rule mounts right onto the mercury barometer itself. It allows the officer to easily dial in the latitude, height, and temperature to quickly read the fully corrected pressure at a glance. It's a fantastic analog life hack.
And our final stop, Section 6, taking sea surface temperature. This last instrument takes us out of the air entirely and directly into the ocean right beneath the hull.
While modern ships can easily read water temperature from their internal engine room intake, that water is often artificially warmed by the ship itself. So, to find the truest sea surface temperature, mariners step out onto the deck and lower a specialized rubber or canvas bucket directly into the sea. They let it stabilize for about a minute, haul it back up to the deck, and immediately insert a thermometer. They have to read it within 30 seconds before the ambient air temperature skews the sample. It is a highly manual but incredibly accurate process.
The meticulous routines we've explored today, from swinging a psychrometer by hand, to observing the trace of a barograph pen, to calculating latitude gravity corrections on a gold slide, they remind us of something pretty profound. True navigation is an intimate, hands-on dialogue with the environment. As we inevitably hand these tasks over to automated digital sensors, we definitely gain convenience. But we really must ask ourselves, what vital connection to the raw forces of nature do we lose when we no longer manually measure the elements ourselves? Something to think about. Thanks for joining me on this explainer, and I'll catch you next time.
If you are a deck cadet or preparing for maritime exams, subscribe to Deck Cadet Academy for more simple COLREG, navigation, and seamanship lessons.